Welcome to the Hughes Communications Lab of the University of Maryland at College Park. I'm Alejandra Mercado. I'm Associate Director for the Masters in Telecommunications program at the University of Maryland at College Park. I'm also an instructor, a mentor, an administrator, and a lab coach. The Hughes Lab provides hands-on experience where students learn to work with the ETIS B210 software-defined radio, as well as the GNU Radio Companion, which is a front end to the GNU Radio libraries for digital communications and signal processing.
Last time we did AM modulation. This time we're going to do FM modulation. M of T is the information bearing signal, and that is usually baseband, and it can be anything, voice, music, anything you like. The frequency modulated signal will be carrying the information M of T using the angle. So the FM modulated signal will have an amplitude, and that simply indicates how strong the signal gets. It doesn't have any part of the information M of T. The unmodulated carrier frequency 2 pi FC is the center frequency for the FM signal, and M of T will reside in the phase. So the FM signal will carry the information bearing signal inside of this phase in this format. M of tau will be integrated from time 0 to t, and that integral will be multiplied by 2 times pi times the frequency sensitivity, which is a known constant. What we saw last time is that in an AM modulated signal, the information bearing signal M of T is carried in the envelope of the signal. Whereas now, for a frequency modulated signal, the information bearing signal is carried in the frequency, or you can see it reflected in the zero crossings of the signal. But as mathematically intriguing as that is, it's not very intuitive at all. How would a receiver recover M of T in this situation? Let's assume that we are at the receiver. SFM is our FM signal, and the information bearing signal is being carried in the frequency as we've discussed in the previous slide. But this is a broadcast environment, so we're also going to have other signals being carried on other frequencies. We'll call all the other signals that are outside of the channel we're interested in out-of-band signals. And in addition to all of the out-of-band signals, upon arrival to the receiver, the signal is inflicted with additive white Gaussian noise with power spectral density n naught over 2. The first thing that happens is going to be feeding the collection of all signals and noise through a bandpass filter. This bandpass filter, as we saw in the previous video, will leave our desired FM signal untouched, but it transforms the white additive Gaussian noise into narrowband noise affected by the bandpass filter. Again, if you don't remember this, I urge you to go to video 2 and review what the bandpass filter does. Next, this new signal that has isolated our FM signal and the narrowband noise is fed through a frequency discriminator. Let's go ahead and study what the frequency discriminator does. Zooming into the frequency discriminator, we're reminded that the input to this frequency discriminator is our FM signal plus narrowband noise. And inside the FM signal, our information-bearing signal, the thing that we want to get to at the receiver, is embedded in the frequency of this FM signal. Now, the frequency discriminator has three principal parts: a bandpass limiter, a differentiator, and an envelope detector. The input to the bandpass limiter is X of T, which has our FM signal and narrowband noise. Let's call the output of this V sub 1 of T. And let's zoom in to see how this particular block works. Now, due to path loss and fading experienced in the channel, the amplitude of our FM signal is no longer the constant that was designed at the transmitter. It is now a time-varying variable. But for reasons that will become apparent very soon, we need this amplitude to be a constant. Now, we shouldn't care what constant, because M of T, the information bearing signal that the receiver is trying to extract, is not riding on A sub C. It's actually in the frequency of this signal. So we would like to replace this time-varying a sub c of t with just some constant, any constant, we don't care which. The bandpass limiter's job is to perform clipping and filtering to replace that time-varying amplitude with some known constant. So after the bandpass limiter, the output v sub 1 of t is the same as the input x, except for the amplitude a sub c of t, which was time varying, has been replaced by a known constant. Let's call it c. So next, we're going to see what happens when v1 of t is fed through the differentiator. But in order to do that, let me just move this output v1 of t to this other location so that it'll leave us a little bit of space to work with. The output of the differentiator is simply the derivative with respect to time of the output of the bandpass limiter v1 of t. Now we see the benefit of the bandpass limiter because c is a known constant, and due to the linearity of differentiation, it can just be brought out of the derivative. If we hadn't used a bandpass limiter, we would have had to take the derivative of a sub c of t times cosine of a function of t. We would have had to invoke the product rule, and we would have ended up with a number of products that were unnecessary, especially since m of t was not in a sub c of t. Now, the known constant c of t is just pulled out of the derivative. Now we take the actual derivative of cosine of a function of t. We invoke the chain rule, and we say that the derivative of a cosine is minus sine. And then we multiply that by the derivative of whatever is inside the argument of the cosine, which is 2 pi fct plus 2 pi kf with the integral from 0 to t m of tau d tau. Now once we take the derivative of the argument of the cosine, we're left with 2 pi fc plus, invoking the fundamental theorem of calculus, we get 2 pi kf m of t. Notice that c is known. It's the constant of the bandpass limiter. The carrier frequency is also known. The frequency sensitivity is also known. And m of t is what we seek. It's what we want. And all of these constants collectively are multiplying a sine wave. What does that mean? That this is the envelope of that sine wave. In other words, the thing that we want to extract at the receiver is now riding in the envelope of a sine wave. All we have to do is remember everything that we learned in video 2 about extracting information from the envelope of a sine or a cosine. Once again, we're going to move this expression out of the way to make some space in order for us to study the next block. We're going to now zoom in to the envelope detector. The input of the envelope detector is v sub 2 of t, the output of the differentiator. And we're going to see how the output of this envelope detector will have a very simple function of what we seek, which is m of t. Now, V2, the input of the envelope detector, is now like an AM signal. If you haven't yet seen video 2 of our sequence, I urge you to pause this video and go back and watch video 2, which explains how an envelope detector extracts the information-bearing signal m of t from the envelope of a sine or a cosine. The output is going to be the envelope, which is minus c, a known constant, times 2 pi times the carrier frequency, also a known constant, plus 2 pi times the frequency sensitivity, also a known constant, times the information-bearing signal m of t, which is what we seek, plus the in-phase component of the narrow band noise, which has been altered, of course, by the bandpass limiter and the differentiator. Let's zoom out again to get a picture of the whole once again. The FM frequency modulated signal arrived to the receiver antenna along with a number of other broadcast signals on other channels with other center frequencies. The output of this receiver is going to be a simple linear function of the signal that we want, m of t, plus some new noise. we're going to open the application that handles the SDR drivers. See video 1 to learn how to install Cubic SDR. The program searches for radios, and we can see our RTL2832U device on the list. Click on it to turn on the SDR as a receiver. We see that the antenna is receiving RF signals across a 200 kHz spectrum. The waterfall plot shows a lot of energy near the 91 MHz carrier. Before setting the receiver as FM, let's do some housekeeping. The sampling rate should be well over 400 kHz, which it is. Before exporting the received signal from the SDR, we'll limit the audio file size to 20 seconds. Oops, I set the FM receiver to the wrong carrier frequency. I'll delete that. Let's try again at 90.9 MHz.
100 million in.
The SDR is receiving WAMU, a local FM radio station. Now we can save the audio signal to a WAV file. We click the lower left corner to record and save the signal. Now we'll exit Cubic SDR and open the audio file for filtering. There are a number of ways you can filter the audio file. I like MATLAB for its graphics, but let me be clear, anyone can follow this video. Say you're a University of Maryland student, but you don't want to download anything onto your computer. You'd rather work in a computer lab that has MATLAB. Where do I find MATLAB on campus? You can work on MATLAB on campus library computers, and here are a list of places where you can find them. Or say you're a UMD student and you do want to download MATLAB onto your home computer. MATLAB is free for UMD students, available for PC, Mac, and Linux. All faculty, researchers, and students can use MATLAB on their personal computers and laptops. Here's a third option. Let's say that I don't want to download anything into my computer and I don't want to come to campus. Can we find MATLAB online? You can connect to the UMD Virtual Workspace. It provides the University of Maryland students, staff, and faculty with a Windows virtual desktop that includes a suite of software applications available for university work, including MATLAB. But what if you're not a University of Maryland student? What if you like MATLAB, but you want to download an open source version that you can use even if you don't attend UMD? You can download the open source version of MATLAB, which uses the same commands and provides some of the same toolboxes. It's called GNU Octave. First, I like to clear all variables, close all plots, and clear the command window. This step helps if we need to debug later. Next, let's load the audio file we got from the SDR. We call the array that holds the signal FM signal. MATLAB's audio read command also loads the sampling rate used to collect the signal. We're going to use this later to get the signal spectrum. I like to see the raw, unfiltered time plot of our signal, so I'll just plot it with respect to the sample number. Notice that I use MATLAB's subplot command, so I can later compare the raw, unfiltered signal to the filtered signal we're going to have later. And there it is. This is the time domain plot of our FM radio signal collected by the SDR. To see the spectrum, I employ MATLAB's FFT along with the sampling interval. This is a topic we discuss at length in ENTS 622. I use my own function that retrieves the magnitude of the spectrum and the frequency range for plotting. We'll open a different window to plot the spectrum. Now we can start playing. I'll let MATLAB design a digital low-pass filter with a cutoff frequency of 5 kHz. This time I'll select a Butterworth filter since it's maximally flat in the passband. The order of the filter is 15, so MATLAB returns the transfer function coefficients of the order 15 low-pass digital Butterworth filter. The A vector has the coefficients of the transfer function's denominator, and the B vector has them for the numerator. We'll create a new filtered signal by just providing the raw signal and the filter coefficients to MATLAB. Let's run it now and see what happens. I'm going to use the same figure 1 with subplot to plot the filtered time signal right below the raw unfiltered time signal. We can certainly see a change. The filtered version seems to have less energy in the moments of silence. Now let's see what happens to its spectrum. Again, we use the filtered signal and its sampling interval to be able to plot its spectrum. We'll use the same figure 2 and subplot to align the spectrum of the filtered signal right below the spectrum of the raw signal. And there we have it. The spectrum of the filtered signal stops at around 5 kHz, just as we expected after low-pass filtering. Removing the high-frequency content includes removing high-frequency noise, and we wonder if that would be apparent in hearing.
Spawn in Atlanta. Someone came to me and said, you really need to look at this, and I did. I said, yeah, this is impact. Spawn in Atlanta. Someone came to me and said, you really need to look at this, and I did. I said, yeah, this is...
You can keep playing with your script. Change the filter to an FIR filter or an elliptic filter. Change the order of the filter. Change the cutoff frequency of the filter. Listen to how each one affects the signal and the noise. Have fun. Using the FFT to plot a signal spectrum, filtering and different filters and how they affect a signal, bandwidth, noise, and sampling rate are all topics we discuss in digital communications. If you like these subjects, then maybe taking ENTS 622 would be interesting for you. If you really want other electives, then you can still play with SDRs at home.
Here at the Masters in Telecommunications program, we strongly believe that the best student experience involves hands-on labs and projects to equip our graduates to excel in the workplace. One of the things that attracts students to our program is that we are very industry focused. We keep a constant tab on the skills that hiring agents want, and we make sure that we offer courses and labs that provide these skills.